Thank you very much, Ulf. I want to say before plunging into the topic itself that I'm very fond of Sweden. I lived here for 6 months quite a long time ago, actually 52 years ago, and fond of the culture, the people, the language, everything, and so it's a great pleasure to be here. And it's an honor to speak in this wonderful room. And I don't know if other people this year have mentioned it, but this is, 2018 is the 100th birth year, or it's not the 100th birth year, the 100th anniversary of the birth year of Kai Siegbahn over there. Let's see if this works, right there. And that's Mana Siegbahn, I assume that's his father, right? The one right there. Yeah, and so it's as I recall, Kai Siegbahn was born on April 20th of 1918, and so it's an appropriate year to be in the Siegbahn Hall. I know that it's interesting to me. I met Kai Siegbahn on a number of occasions, and the last time was about 22 years ago, and I noted that some of his work that he was well known for was in measuring aspects of the Compton effect, which was actually something I talked about in my earlier lecture on Einstein. And that's a very interesting thing because it binds him, in a certain sense, with my father, who was a physicist and who worked also in his early days on measuring the timing of the Compton effect. So that's something they had in common. And I know they knew each other. They met on many occasions. So I want to mention also that today happens to be my father's birthday, by coincidence. And so I thought I would make this lecture in his memory. And he had an enormous effect on me. And in fact, in my thesis, which this lecture is really mostly about, I had many words of thanks, and among the words of thanks, the last closing words of my words of thanks were to my father, and I said this: "Finally, I would like to say that my eternal faith in the beauty and simplicity of nature comes straight from my father, Robert Hofstadter, and has here acted and will always act as the main guiding principle in my view of the universe." And that's certainly true still today. So that's what I wanted to say about my dad. He'll come up a couple of times more in the lecture. Now, this is an overview. I'm not going to read this to you, but basically this, what this lecture does is it tells about how I got into physics by a very circuitous and bumpy route, how I was very happy to be in physics for a little while and then got very unhappy. The unhappiness is starting around here. And then how I got happy again, and then how I got unhappy again, and then how I got happy again. It's a very bouncy story, and it often appeals to graduate students and other young people who are struggling. Of course, no one story applying to one person will apply to other people, but at least it gives a kind of a frame of reference with which you can compare your own travails and debacles as you struggle through your career. So let me begin with the happy part, which is when I was quite young. I was fascinated by mathematics. I particularly loved number theory. And when I was about 16, I started passionately exploring certain kinds of integer sequences. Now this is very relevant, as it turns out, to what comes subsequently. So bear with me for a moment, although it will seem like it's just an excursion in elementary number theory. It is, in fact, very central to the talk. So, well, before I come to the elementary thing, I have to say that I did a lot of the work that I did with friends, and one of my best friends from elementary school was Robert Berninger. Robert and I were both fascinated by mathematics and physics, and Robert always wondered why number theory did not play a role in physics. He wrote a letter in 1969, this is considerably after the number theory work was done. But he wrote the letter asking this question, and the letter got published in a book. The book was this book, The Quotable Feynman, edited by Feynman's daughter, Michelle. She went through a lot of his correspondence and his writings and found some of the most interesting things he said and put them into this book. And I happened to come across Robert's question, which I didn't know he had written a letter to Feynman. And indeed he had, and Feynman answered it. And here is the quote from the book. "I don't know why number theory does not find application in physics. We seem to need the mathematics of functions of continuous variables, complex numbers, and abstract algebra." But he didn't believe, and very few physicists ever thought that number theory would have any connection with physics. So they thought. So the work that I did at Stanford in the early 1960s was largely experimental or empirical, if you wish. In other words, I did a lot of calculation, and I used this old calculator that my dad did his income taxes on. That was, but then I used a Burroughs 220 computer later on at Stanford, and then I used other computers as Stanford got more and more sophisticated in the world of computing. So what kind of thing did I explore? I explored what I called eta sequences, but you can call them sidewalk sequences. So what I'm going, it's just a very simple idea. Imagine that there's a sidewalk whose squares are of side 1, exactly 1. We're talking precision now. And I'm going to take steps on this sidewalk that have length square root of 2, and to every digit, you know, all the digits of the square root of 2. So when I walk, I'm walking so perfectly, and I'm crossing a couple of lines, 1 or 2 lines of the sidewalk, because the sidewalk squares are a little bit smaller than my steps. So what happens? Here is alpha is the step size, and those red dots are showing you where I land. Of course, it would be infinitely precise. And as my steps go on, I cross in the first place here 1 line, then 2 lines, then 1, then 2, then 1, and 1, and 2, and so forth. And so I get a sequence of 1s and 2s. Of course, those are the 2 integers that surround the square root of 2, which is 1.414. The closer one is 1, and the second closest one is 2. The 2s occur separately, that is, isolatedly. The 1s, however, occur in little clumps, you might say. These clumps are small, but sometimes of size 1 and sometimes of size 2. But anyway, that's what they look like. Here we have a phenomenon that involves 2 competing periodic phenomena. One is the periodicity of the sidewalk, and the other is the periodicity of my steps. And so we get something where 2 periodicities are sort of fighting with each other. Now, I call the second closest integer, the one that is farther away from the square root of 2, the sep, because it separates the groups. And I call the other integer, the closer one, I call it the coun. And you can think of coun as being the thing I count. I'm going to count those things, and you'll see in a moment. But just so that it's easy to remember, coun begins with the letter C, and it also is the same C as in closest integer. And sep, for separator, begins with the letter S, and it's the same letter as second closest. So those are a little mnemonic for remembering what a sep and a coun are. Okay. So, oops, I went the wrong direction. What I'm going to do is I'm going to do what I call taking the derivative of the sequence, which means I count the number of couns between seps. Okay, so that's 1, 2, 1, 2, 1. Now I'm going to show you a more general case, because this turns out to be a very special case. I'm going to show you a more general case of a number where alpha is no longer the square root of 2, alpha is some number between 6 and 7. So here is the eta sequence that belongs to that number. It has couns of 7, those are the second closest integer. I said counts, I meant seps. The seps are the 7s and the couns are the 6s. And there they are occurring, four of them, then 4 of them, then 3 of them, then 4 of them, and then 4 of them. And so I count. I'm taking the derivative here. And what I get is another sequence consisting of 2 integers, which looks suspiciously like another eta sequence, belonging, however, to a different number, not belonging to this number alpha, but to some other number, which we could call alpha prime. Is it an eta sequence? And the answer is yes. So this is what I called the fundamental theorem of eta sequences, which is when you take the derivative of an eta sequence by counting the counts between the steps, you get another eta sequence. Eta prime of alpha, that's the derivative, is eta belonging to another number, alpha prime, where you can get the alpha prime by this simple formula, which is the sep minus alpha over alpha minus the count, and that means basically the distance to the second closest integer over the distance to the closest integer, so it's another real number over greater than 1. So what you do then is you can take alpha and get alpha prime from it, and then of course you get alpha double prime and alpha triple prime, and you can keep on going. You can go on forever if alpha is irrational. And we'll temporarily just assume alpha is irrational so that this will go on forever. Now these real numbers will be accompanied by the counts and seps that are attached to them, the closest and the second closest integers to them. So there they are. This is a column of integers, and this is a column of integers, and these are the second closest, and these are the closest. And for any real number you can do this, as long as it's irrational. You can do it for rationals as well, but it will terminate. So that is that's what these columns are, real numbers and integers. Now, let's take an example. If alpha is the square root of 2, it turns out that the derivative sequence is the exact same sequence. So in other words, alpha prime equals alpha, and that means that alpha double prime, of course, equals alpha as well, and so forth. So you just have the square root of 2 going down infinitely many times. The counts are always 1, and the seps are always 2. And that's a very simple example of this phenomenon. Another very famous constant that is located between 1 and 2 is the golden ratio, 1 plus the square root of 5 over 2. And it turns out that it has the opposite columns, that is where it's closer to 2 than it is to 1. And so its counts are always 2, and it's its own derivative, so the seps are always 1. So there's a curious complementarity between the square root of 2 and the golden ratio in this case. And it might open up a question in more general terms of what happens if you swap the 2 columns. What number do you get that if alpha is given and you get the column, the counts and seps, and you swap them, what number beta will have that as its counts and seps? So that's the question. I called that function int. In this case, the square root of 2 is int of phi. Phi is int of the square root of 2. But in more general terms, you would say, okay, alpha gives these counts and these seps, flip them, cross them. Now what number beta is such that it has those? And alpha equals int of beta, beta equals int of alpha, int for interchange. Interchange the 2 columns. That was this function that I invented. Now I did lots and lots of things in these several years that I was exploring number theory like crazy. This is only a very small part of what I did, but it turns out that it's the most relevant part, and so it's important for me to tell you about this. Now, what does this function look like? When I was first calculating it, I did it all by hand, and then I did it with the help of the little calculator, and then I did it with the help of a computer. I didn't have computer graphics. I had to graph it all by hand. This is, of course, a much later graph done by a computer, and it shows you the solution, which I did not see at the beginning. I only saw, what I saw was something that looked like this, but it was much blurrier, and it sort of looked like a little bumpy thing that went along and then kind of took a big leap here, and then kind of bumpy here. I couldn't tell what was going on. Later on, I kind of realized, I came to understand what was going on. and I'll tell you about that momentarily. So I just want you to take a look at this, because this shape, this thing where it gets these ribs, we could call this a rib and another rib and another rib. As they go toward the corner, they get smaller and smaller. And also, this is a little curved, and this gets a little less curved and a little less curved. So they get a little bit less, they get a little bit straighter, you might say, and they get shorter and they shrink as they go toward the corner. That's a telltale phenomenon that occurs later in this talk. What I wanted to say is that, that this is between 0 and 1. The same graph repeats itself here, up here between 1 and 2, and then between 2 and 3, and so forth. So this is really the main phenomenon. And if you look at it, you will see that the ribs themselves are composed of sub-ribs. And of course you can't see, but the sub-ribs are composed of sub-sub-ribs and so forth. So it turns out to be a structure that is made of copies of itself, albeit distorted copies, because this is straight. That's a straight diagonal, whereas this is curved. And so is this. Each one of these is curved, but they're curved less as they get down toward the end. So what we can say is that int consists of copies of itself, but that are bent. I might explain that the flipping of the counts and seps is responsible, the top level flipping of the top count and sep is responsible for this anti-diagonal. The second level flipping of count and seps is responsible for these ribs. The third level is responsible for the sub-ribs, etc. So each level that you go down gives you another nesting, and so forth. So int is composed of infinitely many smaller and distorted copies of itself. That was exciting to me. It was a discovery I made at some point, and I proved these results. I was very, very diligent about trying to prove everything that I discovered, and it was very exciting and really intoxicating, I would say, for a young person to be discovering these things. And I felt that I was going to go on and be a number theorist, and that was my great hope. And so I went on to graduate school. Last thing about int before I quit here. Int takes a jump discontinuity. Let's go back here, maybe to here. It takes a very big jump discontinuity here at a half. This is exactly a half. And also at a third, and also at a quarter, and also at a fifth, and also at 2/3, and at 3/4, and at 4/5, etc. So it takes jumps at rationals. It takes also at 2/5, at 3/7, and all sorts of places. So it takes a jump discontinuity at every rational, but you could say it takes a jump discontinuity that is related to how big the denominator is. And as the denominator gets bigger, the jump gets smaller. So for an irrational number, if you think of an irrational number as being sort of a limiting process of getting bigger and bigger numerators and denominators, then the irrational number is sort of an infinite integer over another infinite integer. So the jump discontinuity turns out to be of size 0, meaning it is a continuous function at all irrationals. That's an interesting quality of int. Discontinuous at all rationals, continuous at all irrationals. Now, I went to graduate school at Berkeley, which was a very good school. However, I was required to take courses that were very abstract, and to my great surprise, I found them too abstract, and I couldn't relate to them. I couldn't see images. I couldn't understand what I was being asked to absorb. I had to do this as a fledgling graduate student, and it was extremely traumatic. I will tell you. It was very, very upsetting to me. Number theory, I took a course in number theory, and they never mentioned the integers. I mean, you might say they mentioned integers, they mentioned numbers of some sort, but they were very high abstractions. They were not my familiar integers that I loved. And I got more and more upset, and finally I realized I just had to get out. Mathematics was not going to be my future as I had hoped it would be. And that was a very, very difficult time in my life. But I made the decision to make a leap away from mathematics and also away from Berkeley, which at the time in the mid-60s was a hotbed of extreme political activity, which was just a little bit too intense for me. And so I took this leap, and 1968, And this is the leap I made geographically from Berkeley to Eugene, Oregon. And I took the other leap simultaneously of going from mathematics to physics, or if you wish in particular, from number theory to particle physics. There's a Feynman diagram to symbolize particle physics. And I was making this leap, but as I said, I didn't just make it from math to physics. I made it deliberately into particle physics because I was suffering from a prejudice. A prejudice that I later found out was definitely a prejudice, which was that physics is only about particles. All the rest of physics is just engineering or not serious stuff. The serious stuff is particles, or maybe general relativity. But other than that, that was what physics was. Other than that, there's nothing but that. So, now, in this very auditorium a couple of months ago, Shelley Glashow gave a very fun talk about his days, which were somewhat earlier than mine, but nonetheless he said, and I quote, particle physics was easy in those days because there was so much low-hanging fruit. Well, maybe so when you have an advisor like Schwinger who hands you a perfect thing and says, work on this problem. However, it wasn't so easy for me, and I'm going to tell you a little bit about it in my position. So here we are, lost, up in Eugene. We had a preprint library in the Institute for Theoretical Science, and this would be about how much came in every week. And it was very, very difficult to figure out what to read and what not to read. I call it the vast reverberating din. Here are some of the particles, for example, that were in the air at that time. Quarks and gluons and pomerons and prequarks and partons and instantons and axions and gravitons and solitons and tachyons and gravitinos and goldstone bosons and Higgs bosons and squarks and photinos. Quite a number of things for a graduate student to try to understand and make sense of. Not to mention regipoles and magnetic monopoles and the Veneziano model and Majorana neutrinos, and I'm not going to read it all, I swear to you. But these are some of the things that were coming in that pile of preprints every week. And so were these things coming in, quantum flavor dynamics and spontaneous symmetry breaking and neutrino oscillations and asymptotic freedom and the Cabibbo angle and the renormalization group and Burkane scaling and the Weinberg angle and Susie Guts and Planck length and PCAC and SU3 cross SU3 and dispersion relations and quark confinement and SU12 and QCD and lattice gauge theory, etc. Not to mention strangeness changing neutral weak currents, unitarity violating deep inelastic processes, Cabibbo Kobayashi Maskawa matrix, Adler-Bell Yakiv anomaly, relativistic superconductors, running coupling constants, and so forth, ad nauseum. I found myself at my wit's end, and I changed from, signal to noise problem. How can you recognize the great gems in the gigantic garbage dump? How can you know what to follow and what to ignore? And it was unbelievably difficult. I jumped from one advisor to another, to another, to another, and found nothing to give me clarity. The big day was December 14th, 1973, when I had been asked to give a talk on a paper that was about something in gauge theory, and I did my best to read it and to summarize it, but I hated the paper because in this paper they introduced 156 new particles in one fell swoop. And I was very familiar with the fact that in 1930, Pauli had introduced the neutrino. He called it a neutron because the neutron, what we call today the neutron, had not yet been discovered. And so he was inventing a neutral particle. And he called it the neutron. Later on it was renamed the neutrino by Fermi. But in any case, he thought that in order to save three fundamental conservation laws of physics, conservation of energy, conservation of momentum, and conservation of angular momentum, to save all three of them, he could introduce one particle that would carry away momentum, energy, and angular momentum from beta decay And he was so frightened of this wild, crazy hypothesis that he didn't dare write a paper about it, but instead he wrote a letter to a friend about it, and the friend read the letter out loud in front of a conference. And that's how Pauli's idea became known. So my point is that Pauli, to introduce one particle, and he was one of the most brash physicists imaginable, was very frightened. And here are these physicists inventing 156 new particles for almost no reason. And I said to the people that I was giving this presentation in front of 10 people or something like that. And when I came to this point, I said, these people have no sense of shame. And I threw the paper on the ground, and I walked out, and I said, I quit. And at that point, I was lost. And this blank slide represents that I had invested 6 years at that point of my life into particle physics, and I had nothing. And I thought, I'm never going to get a PhD. What am I going to do? What can I do? It was a very, very frightening moment. So it happened that my dad had, at Princeton, gone to a graduate school there where a Swiss physicist, a very distinguished Swiss physicist, was a solid-state theorist, was there as a postdoc. And my dad, it happened that Gregory Wanye was at the University of Oregon. So when I first went to the University of Oregon as a gung-ho particle person, I introduced myself to Wanye. He was always extremely polite to me, very nice, and invited me to his house for dinner several times. So I got to know Wanye, but I never dreamed that I would ever think of having him be my advisor, because to me, going into solid state was slumming. It was going into the slums of physics. How could I even imagine such a thing? This was my prejudice. This was my very deep prejudice. Now, I got out of this prejudice because of 3 people. My first was my great friend Pete Rimby, who was in graduate school with me, and he just simply said, Gregory Wanye is one of the deepest physicists alive today. Well, that was a pretty serious statement I took very seriously, because I admired Pete. My great friend Francisco Claro from Chile said, solid state is a wonderful subject because it builds a bridge between 2 worlds, the microscopic and the macroscopic. I had never thought of it that way, and I was also very impressed by that. And by the way, Francisco did his work with Gregory Wanye. And then finally, the last person was an unknown Stanford physics graduate student who I was speaking with one day. And this person made this amazing remark. He says, particle physics has only one vacuum, the continuous vacuum of empty space, but solid state physics has many vacuums. Every single crystal is a different kind of vacuum. And this was a poetic and beautiful thought, because it really was saying that a crystal is like a medium, which is a discrete medium, as opposed to a continuous medium. It has a periodicity, it's not isotropic the way space is. It has preferred axes. And it all of a sudden it reminded me of number theory. It reminded me of the distinction between the real line and the lattice, the one-dimensional lattice of integers. So in some sense, number theory is kind of like solid-state mathematics. It's a one-dimensional crystal superimposed on the vacuum, the real vacuum, which is the real line. So all of a sudden, I started seeing solid-state physics in a completely different way. It wasn't slumming at all. It was something quite beautiful, closely related to number theory. Well, then could I go swimming with an Oregon duck? Well, I say Oregon duck because that's the mascot of the University of Oregon. So there's a picture of Wanye, and he said to me when I went to him to ask him if he might possibly be interested in having me as a graduate student, he said, I have 3 problems for you to consider. I don't remember the first 2 that he told me about, but I vividly remember the other one. It had to do with Bloch bands in a crystal. I'll mention Bloch bands, discovered by Felix Locke in 1928, that electrons in a crystal have a continuum of energy values forming a band. This is a set of continuous band of energy levels that are allowed, and then above it, suddenly there's a gap. And below it, there's a gap. So there's a band. This is called a Bloch band. forbidden energies and allowed energies. I might say that Felix Locke was at Stanford, which is where I grew up, and he was in the same department as my dad, and in fact he was my dad's closest colleague, so I had known Felix ever since I was a little boy, and he was a very close friend of our families. And here's a picture of my dad and Felix having just climbed a wonderful peak in the Sierras in 1953. My dad is on the right and Felix is on the left. So these are two very dear people to me. Now, the other thing the problem that Gregory Wanye was describing to me had to do with Landau levels, which is when you have electrons not in a crystal, but just in empty space, and you ask what are the energy values of electrons in such a circumstance, electrons in space in a magnetic field. And the answer is that they are evenly spaced, and then there's a gap between these evenly spaced levels. Those are called Landau levels. So the natural question was to combine the two situations, in other words, put the magnetic field onto this discrete vacuum. And what happens now with electrons in a crystal in a magnetic field? And it was a very fundamental problem. I mean, basically, you're taking electrons in a vacuum. I put it in quotes because it's a crystal, but it's a discrete vacuum, and just applying a magnetic field to it. What could be more natural question than that? However, it's not at all easy, and it had been 40 years that the problem was first posed, and it still didn't have an answer. Here is a picture with, just imagine that the crystal is only a two-dimensional crystal of a square lattice, A on a side and A on the perpendicular side. And so we look at the flux that passes through a lattice cell. That flux is the magnetic field times the area of the cell of the lattice. Now it turns out that nature hands us a unit of flux that is natural, the so-called flux quantum. The flux quantum is a product of h, c, and 1 over e. It's a natural amount of flux which occurs in physics, and it's a natural measuring tool to measure other fluxes with. So if you divide the flux that I already spoke of, a squared h, by this natural unit, you get a pure number that measures the magnetic field in terms of the magnetic flux quantum. Okay, this is a fundamental number, this alpha number, for electrons in a crystal, a square lattice in this case, in a magnetic field. And so that number is this key number in this situation. And Gregory said to me, it turns out that rational and irrational values of alpha act differently. Now this sounded to me absolutely crazy, and I couldn't believe it. Obviously, how can nature think of take into account all the infinitely many decimals of a real number? I mean, no number is defined that well. It made no sense. But he said that it turns out that this is a fact. This is well known. It's been studied, and people have studied this for many, many years. And I didn't believe it. I just thought, surely you're joking, Mr. Wanye. Rational and irrational. And so that, of course, reminded me of my old work having to do with int and with many other things that I had explored in those number theory days. And I thought to myself, go for it. It's a good chance. Maybe some of your experience will come in handy. I didn't know. I was just taking a wild guess. So I had to retool myself and become sort of familiar, at least a little bit, with solid state physics. And I had to learn about these kinds of things that exist in solid state physics. So I'm going to focus down on just two of them because they have to do with two crucial people, Bloch and Wanye. A Bloch state is the most fundamental state of an electron in a crystal. It's a sort of a standing wave that is distributed over the entire crystal, and it has a phase factor that is sort of e to the I kx, where k is a wave number, that kind of goes like this, a helix, as you go down the crystal. And it didn't elude me that the word helix for this phase factor rhymed with the name Felix. And so I will show you that in a moment. Gregory Wanye took these Bloch states and he took the Fourier transform of them, and that made them localize on a single atom or on a single nucleus. These became known as Wanye functions or Wanye states, and they're often used as an alternative to Bloch states to expand wave functions. So I decided I would write a limerick about Felix. He was actually Heisenberg's first PhD student. A Heisenberg student named Felix thought crystals were swell psychedelics. It boggled his mind when he happened to find that a Bloch state repeats mod a helix. Then I wrote one about Gregory Wanye. The physicist Gregory Wanye left his land for the US of A. There in solids with lots of not waves but dots, he transformed Bloch functions away. So I had fun. I wrote limericks about my fellow graduate students. I wrote limericks about my professors, and I was having fun. While I was not doing limericks, I was actually very involved on another project that was taking time away from Torah, as they say. I was working on a book called Gödel's Theorem in the Human Brain. That wasn't the eventual title that it had, but that was the title that I was using. And it took a great deal of time. I really was working on it far too much. I got very scared that I was not going to finish my PhD if I kept on working on this book. So recently I discovered in a box that I had not looked at in some 30 or 40 years, this document. I guess it's 40 years. This was written up in 1974 at some point, so it's actually 44 years ago. I don't know if you can read it, but it says Society for the Sanity and Survival of DH, and that's me, Constitution. And it consists of a whole bunch of handwritten rules, including penalties that I would have if I did not work on my PhD thesis every day. And I had all sorts of rules, monetary fines that I would impose on myself. And I put my manuscript of my book, Gödel's Theorem in the Human Brain, which of course became Gödel-Escher-Bach, but I put that manuscript into a drawer, and it was very severe penalties for opening that drawer. So that's an interesting moment in my life. I actually didn't touch the manuscript for well over a year. Didn't do it at all. In 1974, Gregory Wanye was going to Regensburg, Germany. And I asked if I could come along, and he worked out for me to be able to come. And I there was a Verwalter der Dienstgeschäfte eines wissenschaftlichen Assistenten, meaning teaching assistant, in the Lehrstuhl Obermeier. Gustav Obermeier was the director of this particular part of the physics department, and so here we have the four people that formed this little group. You may be able to recognize one of them. So that's me. Alexander Rau was my best friend while I was he was a young professor. That's Gustav Obermeier, who ran the group. And there's Gregory. And we worked on this problem together. Now, the thing about it is that the three of them, the three on the right, were all really master manipulators of differential equations and hypergeometric series and all sorts of things, whereas I was not. And I was always, whenever we would meet in somebody's office, I would sit around feeling very inferior. But I did have one advantage over them, which I will come to in a moment. But now we plunge into the physics of this problem for a while so you can understand what the situation is. What is the Schrodinger equation for a physical situation that involves an electron in a crystal in a magnetic field? So we need a Schrodinger equation. So we need a Hamiltonian. So we start with a Bloch band, which means that for every wave number, kx, ky, a two-dimensional crystal, there is an energy that is the energy inside the band. So given a wave number, as the wave number varies, the energy varies and covers the entire band, A being the lattice spacing. This is the simplest possible Hamiltonian for a Bloch band. not a Hamiltonian, energy function for a Bloch band. We're going to use this energy function to create a Hamiltonian. So in order to make an operator, a Hamiltonian operator, out of a classical number, we use the Dirac recipe of substituting for a number, an operator, a differential operator, from a C number, as Dirac called them, to a Q number, as he called them. And the momentum becomes h bar over I times del, the differential operator. And if there's an electromagnetic field, then we have to add on this term. This is the magnetic vector potential from which the electromagnetic field can be derived. And so this goes to that. This operator goes to that operator. So we want to ask, well, what would be the vector potential when you have a uniform magnetic field? And the answer is, there are many answers. There are different gauges that work. But we took the Landau gauge, the simplest way of getting a constant magnetic field. The curl of this vector potential is a constant field in the z direction. So that was our vector potential. Now, what we're going to do is we're going to perform the Dirac. We're going to figure out how to perform the Dirac substitution on that energy function. So we begin with the energy function, which is the Bloch band. And what we first do is we simply multiply and divide by h, or h bar. And so in the numerator, we have h bar kx and h bar in the denominator. But h bar k has the dimensions of momentum. And it's called the crystal momentum. It acts like a momentum, or it's sometimes called a pseudo-momentum, as it says here. And so it reminds people of momentum. So what if we substitute, what if we just do some magical thinking and replace h bar k, which looks like and feels like and acts like a momentum, by that expression p minus e over c times a, which is a momentum-like quantity. So we just do that. We just go in here, barge in, and replace that by that, which has no legal validity, but it's just a magical act to do. And now we do another substitution. We do the Dirac substitution. We replace a C number by a Q number. In other words, now we put in differential operators. We replace the P by d by dx times h bar over I. There, a sub x is 0, so that goes away. A sub y is not 0. It's this little quantity here. And here we have another differential operator. And there we have something quite interesting. Now we replace the cosine by sum of two exponentials, and we expand. This cosine, this factor 2, gets rid of the factor 2 that there would be down here. And so this becomes e to the a times d over dx, d by dx, and so forth. We have some phase factors here that come from right there. But it looks like that. Now, if you look at those two differential operators, you will recognize that these are translation operators along the x-axis, and they translate by an amount, the distance a. So this is really moving to the right by a, this is moving to the left by a, this is moving straight up by a, this is moving straight down by a, and these have phase factors. So this is our Hamiltonian that we've created. Out of the Bloch band, we've created a Hamiltonian, and now given the Hamiltonian, we can make a Schrodinger equation. So what is the Schrodinger equation? It relates 5 points in the crystal to each other. It says the wave function here, which is psi at xy, is related to psi at x plus a times y, that's that one, and also that one, and also that one, and also that one. It's related to those 4 neighbor points with these, just as a sum of these with phase factors right here and here. That's a pretty stunning equation. Now we can try to make it look more discrete. Oh, well, this is just reminding you of the two different axes. Okay, we can try to bring out the discreteness by replacing x by ma, because we're just talking about points on a lattice. So integer times a, integer times another integer times a. We should use alpha to replace the magnetic field. So we have alpha, and then we'll put e over e0 is epsilon. That's a dimensionless energy variable. So the equation that I just wrote down looks like this now, written in this new form. This is integer subscripts, 2 integer subscripts, and this is still the Schrodinger equation. Now we're going to make a guess that there can be a periodic behavior along one axis. We're just going to assume that it might be periodic, purely periodic along one axis, so that we could simplify it down to one dimension. If we do that, separation of variables, we assume that this is the behavior along one axis. What does it do if we plug in? And I won't do the math, but here is the result that we get. We get a one-dimensional equation. In other words, with one integer subscript now. And it says the wave function at this point is related to the wave functions at these 2 points by this very simple-looking equation. This is called Harper's equation, found in 55, also by Harper, and also found by Wanye at that same time. Now, this thing here is an analog to del squared in the normal Schrodinger equation. It's basically, that's a second derivative. This is a second difference. So it's a difference equation instead of a differential equation. But this is the counterpart to the second derivative. And here we have something that is acting like a potential energy. And the cosine represents the crystal, or if you wish, that's kind of like the sidewalk, and with its regular behavior. And the magnetic field is there, alpha. That is not got the. If alpha were an integer, then it would be like the two things are. The two periodic phenomena are not competing. But alpha is an irrational number in many cases, or certainly not an integer. And so you have sort of two competing phenomena, two competing periodicities, the spatial periodicities. One is the one having to do with the crystal, and one having to do with the magnetic field. And this is the energy eigenvalue. So that is that's the Schrodinger equation right there, and we can see sort of traces of the crystal and the magnetic field. And so these are the 3 points that are related to each other by that. The wave functions at those 3 points are related to each other by that equation. And if you rewrite the equation so that all the two factors of G sub m are put together in a bracket, then you get a recursion relation. It says that this one is formed as a sum of these two, where this one is modified by a product. Now, again, if alpha is an integer, then this thing is just a constant. So we just have a constant, and it really is almost like the Fibonacci sequence. If alpha is not an integer, then this number varies, goes back and forth and back and forth. But it's a very simple recursion relation. And so we can rewrite this in terms of little pairs of numbers. If you take 2 of them at a time, G sub m plus 1 and G sub m, and relate it to the preceding one to the left, then there's a little matrix, a little 2 by 2 matrix, mostly consisting of constants, ones and zeros. But with this here, and let me just remind you that epsilon is the energy, which we'll assume is constant. Alpha, which you may not be able to make out here, but that's an alpha. We have a 2 pi, that's just sitting there. And then alpha is the magnetic field, and then m is an integer. That's the one variable in this thing. So here I'll just show you how it looks. If we have the real line, then those two, if we multiply, let me just go back for a moment. I said I'd call this matrix A sub m, because the m is right there. So this is a function of m. It changes as m changes. So if we multiply by a sub 1, that brings us to there. And if we multiply a sub 2, that brings us there. And we keep on multiplying. Each time we take a new matrix and we multiply, and we get the wave function moving to the right. We get the new wave function at these pair of discrete points. Well, for what values of the energy will this process yield a non-divergence? In other words, as we go out very far away, for certain values of the energy, this will not blow up. The wave function will not blow up. For other values of the energy, it'll blow up, and that'll be physically unacceptable. Okay, well, I guess I have to take an example. 1/3. If alpha is 1/3, that's a certain magnetic field in a dimensionless fashion. Then it turns out that, because of the periodicity of the cosine, this matrix is identical to this matrix, and this one is identical to this one, and this one is identical to this one. So we have these equations. So in fact, this product of 3 matrices is the same as this product, and it's the same as this product and this product. So in fact, we're just putting a matrix to a high power. We can call this A now, and we're just putting A to a high power. So if we want to go very far out, we just put A to a very high power. When will this blow up for large M, and when will it stay bounded? Now, it turns out, as Gustav Obermeier showed, that there is a simple condition on the matrix A, which is a product of, well, I guess I should have said, in the case of 1/3, it's a product of 3 matrices. If it were 2/5, it would be a product of 5 matrices, because for a rational value, then when you plug in that thing under the cosine, it'll come back to itself. And so when it comes back to itself, then the matrices repeat, but it comes back to itself only after 5 times whatever the denominator of the rational number is. So for rational numbers, we'll have this matrix A, which is a product of Q different matrices where Q is the denominator. If alpha equals P over Q, a ratio of 2 integers, then Q will tell you how many matrices you need to multiply by. And the condition on that matrix is that the trace should be less than or equal to 4, a very simple condition. So, and that trace, which involves Q matrices multiplied together, each of which has epsilon linearly in it. When you multiply Q of them together, you get terms that have the qth power of epsilon in them. And so the trace will be a qth degree polynomial in epsilon. Now, here comes my piece of luck. A very, very major piece of luck that allowed me to get into the game, because I was sitting, if you remember, sitting in the office when Wanye and Rao and Obermeier were flinging about their hypergeometric functions and proving theorems, and I was sitting there feeling inferior. Well, it happened that in the Lehrstuhl Obermeier, there was a computer, a little computer sitting on a desktop, an HP computer that I had actually used in Aspen, Colorado 5 years earlier, and I knew how to program it. This is a picture of it. This is the actual computer, by the way. They revived it after 40, whatever it was, years, 43, 42 years in Regensburg when I went there last October. And they revived the actual machine, and it says, "Hello, Doug." It's greeting me. So I programmed this computer to figure out when the trace was less than 4 for a lot of different rational values of the magnetic field. And so let's take 1/3. 1/3 will have a 3rd degree polynomial. And this is a cubic polynomial, so it looks like that. Here's the x-axis going along here. But the question is not where does it cross the x-axis. The question is where is it less than or equal to 4 in absolute value. And so I've widened the x-axis to become what I call a fat x-axis. It's now a thick line rather than an infinitely thin line. It's a fat x-axis. When is this cubic within this gray area? Well, it's in there for this value, set of values of epsilon, right in there. That's when it is crossing and staying within plus and minus 4. Then it goes out and it comes back and it stays in for this length of time, so to speak. And then it goes out again. And then it comes back in and then goes away forever. So there are 3 bands. 3 bands for 1/3. What about 1/5? I'm sorry, here's 1/5. It's going to be a 5th degree polynomial. And this is what Rumpelstiltskin calculated for me. It crosses, then it goes way away, then it comes back, then it goes like this, and so forth. 5 different bands. What about 2/5? 2/5 looks like this. It's the same, it's a quintic polynomial again, a 5th degree polynomial, but the roots are, the fat roots, you might say, are distributed very differently. 2 over here, 1 over here, and 2 over here. And 1/6 looks like this. 1, 2, 3. It tries to get out, but it doesn't quite make it. It goes tangent to the edge of the fat x-axis. It can't quite get out, but it's trying. Then it goes out, and then it comes out again, and then so forth. So you have a little teeny weeny band here, a little band, and then a wide band that touches this wide band, then another one. 6 bands, but 2 kiss in the middle. So in about September of 1974, I was graphing these things by hand. This computer did not have a plotter attached to it. And so I would get out numerical values that it would calculate for me overnight. And I would get out these numerical values. I would come into the office and graph them on paper. And this is what I was starting to see in September of 1974. Well, a couple of months passed. And this is what I started to see in November of 1974. I'll talk about the November Revolution in a moment. So what I would point out is that is what you may recognize from my int graph. In other words, you have something going up towards a corner getting smaller and smaller, and you can sort of see that there's a sort of a periodicity here. I can't explain it exactly, but I intuited that there's something going on here. Moreover, more importantly, oh yeah, well, it reminded me of that. I mean, that's the comparison that I saw in my mind's eye. But also, this little area of the graph, or this one, or this one, or this one, looked to me suspiciously like a copy of the full graph, where these 2 lines that kiss in the middle, this is really 2 bands, even though they touch right there, are those 2 right there. And these 3, these blue 3, are these 3. And these 3 here, these blue 3, are these 3, and so forth. And I thought, my goodness, it looks like this is a little copy. Oh, this line is that line. And this line here is that line. So this is an entire copy of this graph, distorted. And that's what I started seeing. And I call it my November Revolution a posteriori, because at that exact time in SLAC at Stanford and at MIT also, well, it wasn't at MIT, I guess it was, when was it? On Long Island, what's it called? It doesn't matter. Anyway, on the East Coast and on the West Coast of the United States simultaneously, 2 different groups were discovering the so-called J-psi particle, which was a resonance that revealed that there was a 4th quark, a charmed quark. And this was considered to be one of the biggest moments in particle physics at that time. And they later called it the November Revolution, because it was so exciting, because they were discovering that there were not just up, down, and strange quarks, but there was a charmed quark, and later on they would find that there are a couple more. But this was a very, very big moment in physics, and I remember talking to my dad about it over the telephone right at that time when I was in Regensburg and he was at Stanford. And so I was, that's another copy, by the way, a littler copy. And there was another copy right there, and another copy there, et cetera, all the way. So I was starting to see something really exciting here. And it reminded me of that. And I concluded that G-plot was made of infinitely many smaller distorted copies of itself. And I was very, very excited, of course, to find this. And I went to Gregory Wanye and I told him, oh, chance favors the prepared eye. Well, yes, that's the point. I had a prepared eye. Gregory did not. And what did he say? Well, he said, this is numerology. You can do a library thesis. And I said, what is a library thesis? He says, it's where you write up the work of other people. And he said, you clearly can't get a PhD doing what you're doing. But if you really insist, you can put your numerology work in an appendix. And so I was pretty hurt, but I was not deterred. I continued working all by myself, all alone. Now, we went back from Regensburg. One last thing. Yes, my 30th birthday was coming up at that point, and I gave myself an ultimatum. I wanted, because I was very, very concerned with convincing Gregory, obviously, it was necessary to convince him, he was my advisor, I wanted to make a mathematical proof that G-plot consists of copies of itself, and I had done that with int. So I thought maybe I can do the same thing with G-plot. I was hoping that I could. However, I was unable to do it. I worked extremely hard on doing this, but I got nowhere. Then we went back to Eugene. Well, another amazing coincidence took place in Eugene. I was walking by the lab of Russ Donnelly, who was a very good low temperature physicist at the University of Oregon, and I saw a familiar HP desktop computer sitting there with a plotter this time, and I asked him if I could use his computer, and he said yes, nobody's using it, just like Gustav had said, but those days physicists didn't use computers. I don't know why they bought them, because they didn't use them. And so he said, sure. So I used it, and I put that computer to work calculating many, many more values and plotting them for me very precisely using its plotter. And this is what came out in May of 1975. And that was a very stunning graph, and Gregory liked it very much, but he still thought what my ideas were nonsense. He didn't believe my ideas whatsoever about the fact that this was a copy, or that this was a copy. I mean, you can probably see these 4 gaps here, right there, those white gaps. Doesn't that look like that? Doesn't it look like that? You can see it. Well, he couldn't see it, and he didn't believe it for a moment. So what I did was, I took a little teeny copy, what I knew was a copy, down here, that was located, it was, you know, at a funny angle in some kind of funny trapezoid. And I took this thing, which inside it should contain a copy. This is, what does it say, 1/7 and 1/6. So if I go back here, it would be down around here. I don't know where it is, somewhere in there. I took this little trapezoid and I calculated all the values in there, and then I did what I called rectangularization. I turned this thing into a rectangle. I undistorted it, and here's what I got. That's inside that little structure. When I showed that to Gregory, all of a sudden the scales fell from his eyes, and he said, "By God." And he came around, August 1975. And I said to myself, I'm going to get a PhD. That was a very exciting moment for me. So, as it turns out, we've looked at rational numbers, but what about irrational numbers? Well, it turns out that the spectrum, in this case, consists of, if we had for a rational number, p over q, we had q bands. Well, for an irrational number, we should have p over q, where p and q are infinitely large integers, so it should be an infinitely large number of infinitely small bands, and that's a Cantor set. And if you don't know the term, I'll show you what a Cantor set it looks like. You begin with an interval, say 0, 1, eliminate the middle third, then do that to the 2 remaining pieces, eliminate the middle third again, and keep on eliminating middle thirds, and keep on repeating this infinitely many times. What happens at the very end? Anything? Yes, you're left with all the endpoints that you didn't eliminate. And that's an uncountable set. So it's a very big infinity, as a matter of fact, but it's got no intervals in it whatsoever, so it's got a measure 0. So in some sense, it weighs nothing. If this thing had weighed 1 kilo, then the Cantor set weighs 0, exactly 0, but uncountably many points in it. At every irrational field, we have a different Cantor set, because you can make Cantor sets in different ways. You don't have to eliminate the middle third. You can eliminate all sorts of other things. As long as you keep on eliminating things inside the remaining intervals, you'll get a Cantor set of some sort. And so at every irrational field, we have a different Cantor set. And that's what I found and put into my thesis. how to reconcile this weird mathematical object with physical reality. Well, the idea is we have a magnetic field that is not defined to infinitely many decimal places. So if you take G-plot, which is what I called that graph, and you take the union of all the magnetic, the energies associated with all the magnetic fields within a very small delta H, or delta alpha, whatever you want to call it. You just associate a little uncertainty with the magnetic field. Then take all the energy values that are associated with those magnetic fields and take the union of them. Then it turns out that the graph you get, it looks very, very smooth. I call that the smeared graph, because I went and visited Feynman, of all people, in his office in 1975. I wrote him a letter, and he was very willing to meet me. And when he saw this graph, he was so excited he couldn't believe it. He immediately said to his secretary, "Make a copy of this." And he was very excited about it. And I told him about my idea of smearing the graph, and he called it jiggling the graph. Here's what happens if you jiggle it quite a bit. It looks just like a strange black object. I mean, it doesn't have any fractal structure left to it. It's completely continuous. It's like a map with little lakes in it. These little white things could be thought of as lakes. It's just a map of some zone that has lakes in it. If you jiggle it less, you see more lakes and more detail. That's a slightly less jiggled, more precise graph. If you jiggle it less, you get back the original thing. That's with zero jiggling. And now I put this graph on page 137 of my thesis. For physicists, they'll know this number, the reciprocal of the fine structure constant. I couldn't resist this touch. And I guess it shows that I was a numerologist after all. In any case, I wound up deciding that I should be getting out of physics, even though I had had such a lovely discovery. I didn't really think it was going to happen again. I gave a copy to Felix Locke, and when he saw it, he said, when he heard about it, he said, there are two natural frequencies here. One is due to the magnetic field alone, called the cyclotron frequency, and one due to the crystal alone. Two different frequencies. And I had never thought of that before. And I wrote them down, and I saw that their ratio was exactly alpha, two competing periods. So what Felix said to me reminded me of eta sequences, and I was back. So really, I wound up getting a PhD in number theory, even though I had left Berkeley, dropped out. Now I was doing things that I loved. Going out in style. Well, G-plot showed that number theory is intimately linked to physics, and with Cantor sets and other things, it also showed that topology is intimately linked to physics, things that people had not suspected. I was given a referee's report when I submitted my article to Physical Review. It said, "I find this paper delightfully written, almost like a Mozart divertimento." Well, of course, that was, if I can be forgiven for using the phrase, music to my ears. It turns out this is a famous physicist who wrote this. He, 20 years later, introduced himself to me when I gave a talk somewhere and said, "You remember somebody once wrote in an anonymous review that," and I said, "I certainly do." And he said, "Well, I wrote that review." His name, I don't know if you would have heard of him, but his name was Leo Falikov. He was an Argentinian solid state theorist, very distinguished person. So I was very flattered. But I chose to drop out. Why? Well, I had found this very wonderful thing, but I didn't think it was going to happen again, and I thought I might as well go out in a blaze of glory. Now, from then on, G-plot started becoming famous. I never thought of G-plot as going to become famous. I just thought it was my pathway to getting a PhD. It was what allowed me to get a PhD. But it turns out that people started exploring it. In the 1980s, mathematicians jumped into the game, and they changed some terminology. They called the idea that the spectrum for every irrational value of alpha was a Cantor set. They didn't associate it with me, even though I published it in my thesis, in my Physical Review article, and even in Gödel-Escher-Bach. I said it in all three places that it was a Cantor set. They totally ignored that and attributed the hypothesis that the spectrum belonging to an irrational number is a Cantor set to Mark Katz, who made a speech about it at a meeting of the American Mathematical Society. They didn't call it Harper's equation, but the almost Mathieu equation. And in 2009, these two mathematicians, Avila and Zhytomyrská, proved that the Harper spectrum is a Cantor set for all irrational alpha. And in 2014, a Fields Medal was given to Avila in part for his work on this spectrum. And it does show why maybe I wasn't able to do it as a graduate student. It was a very, very, very difficult problem. Physicists all around the world went on a grand expedition exploring variations on a theme. So, for example, this was calculated by Claro, my good friend Francisco, and Wanye. Wanye didn't do the computer work, but Francisco did the computer work, but they put it in a paper. Butterfly for a hexagonal lattice. Butterfly for a triangular lattice. Butterfly for some kind of, I don't know, a model of a molybdenum disulfide lattice. Amazing structures, but they all have something very profoundly in common. Native copies of themselves, nested infinitely many times, distorted copies. Butterfly for a E-braid structure, and I don't know what that is. Butterfly for a kagome lattice, I don't know what that is either, but I think kagome means basket. Butterfly for an octagon and dot tiling, and on and on. It goes, you can find all sorts of variations on the butterfly. Butterfly with both magnetic and electric fields. Then, in 1980, the quantum Hall effect was discovered, and a non-conductor then manifests quantized conductance levels. This was something nobody expected, and it turns out that the butterfly is intimately related. That these gaps that I pointed out to you earlier, I've turned it 90 degrees here, but other than that, it's the same butterfly, just with the gaps colored in now. These gaps can be labeled with integer values in a certain number theoretical way involving Diophantine equations, which I'm not going to go into. These gaps, they're called Chern numbers. And these gaps can be labeled, and they correspond precisely to the conductance levels in the Hall effect, the quantum Hall effect, in the integer quantum Hall effect. So this gap corresponds to this level, this gap corresponds to this level, this gap corresponds to this level, and so forth. All amazing relations that the butterfly had that, of course, I would have never suspected. Now, a woman named Indu Satija, a physicist at George Mason University, even declared that the butterfly is the home, the natural home of the quantum Hall effect. She wrote this book and sent it to me, not as a published book, but as a manuscript, and asked me if I would write something for her about my memories of the discovery of G-plot. And so I wrote something, and that became, it says here, contributions by Douglas Hofstadter, that became my prologue to her book. And so in her book, she talks about all the connections between G-plot and all these different things that I was completely unaware of. Apollonian gaskets, Barry phases, Bose-Einstein condensates, Chern numbers, Majorana fermions, quantum Hall effect, quasi-crystals, renormalization group, topological insulators, abelian and non-abelian anyons, and so forth. All of those things. She also talks about how in the last several years, attempts to empirically to confirm the structure, that the actual physically observed structure is identical to what was predicted. There are all sorts of ways, very ingenious experimental techniques that have been developed to try to confirm it, and pieces have been done, not the whole thing. But it's all way above my head, unfortunately. I got out of physics 40-some years ago. But it's nice to know that it has done all of this. Her book contains all sorts of wonderful things, and I would suggest that you take a look at it if you're interested in this. And a lot of poems. It includes those two limericks that I wrote about Bloch and Wanye. And to conclude, I'll read a poem that I wrote about my experience in discovering G-plot. It's called G-plot's Grace. What happens if a crystal's laced with the lines of a magnetic field? What spectrum will the world be graced with? What energies will nature yield? It turns out that the matter's crux is determined by just what the flux is. P over Q, Q bands begets. Non-ratios, though, give Cantor sets. On hearing this, a physicist will declare it numerology. But once shown G-plot, all agreed deep magic's lurking in a crystal. This gem I found by luck, that's why. There, but for G-plot's grace, go I. Thank you. Oh, thanks. I see I went over time.
No, but it doesn't matter. It's okay. Questions? Yes, over there. I don't know if we have a microphone.
Don't know.
I can try to speak.
Good, very good. Excellent.
So, thank you for this amazing talk. I'm a bit curious about this thing that you locked in the drawer, or like you were punished if you were opening it. In the sense that your rules were how to keep God sane, was it?
Yes.
And my personal experience is that the way to keep me sane is to get into the drawer.
Well, sanity, I know just what you mean. I mean, in some sense, Gödel, Escher, Bach, which is what it became, was much more me than working in physics was. If you look at it a posteriori, you're right that in some sense I needed that more than I needed the other. But I needed what is the word I'm looking for? Sort of a password, or I can't think of the right term. I had to get into. I had to get a PhD. I needed if I didn't get a PhD, what would I have become? I don't know. I'm very serious here. You've raised a very serious question, which every time I look back to that period in my life, and I ask myself, what if Gregory Wanye had not been at the University of Oregon? What would I have done? I certainly wouldn't have gotten a PhD in particle physics. I was totally fed up with particle physics. And I don't think, really, to be honest, I would have been able to get a PhD in any branch of physics unless it had somehow magically tied in with number theory. So I was just phenomenally lucky. And lucky in many ways. Wanye being there, the computer being in the Lehrstuhl Obermeier, the other computer being in Russ Donnelly's office, and of course the fact that I had worked on number theory in the 60s. All of those pieces of luck were amazing. But I think if I hadn't gotten a PhD, I don't know what in the world I would have done, because it was my absolute goal in life, unshakable, to be a professor. And I had to get a PhD. So I was just very lucky. And so I realized my key to getting to the PhD is to work on this damn thing, this damn problem. I mean, because at that time, I wasn't thinking that I was working on a problem that was going to be exciting. I just knew it was going to be a problem I had to work on. So I just said, put that damn manuscript away and work on this damn problem. It was very difficult, but sanity in that case didn't mean in mental sanity. It meant sanity in the sense of, it actually said Society for the Sanity and Survival of DH. And it was for a sort of intellectual survival. But you're right, I should have, and of course I did go back. As soon as I got my PhD, went out. Very good, yeah.
Thanks.
Can you trace your fascination with numbers back to much earlier experiences in life?
Yes, I can. I was always interested in integers. I'll tell you something I remember discovering when I was a kid. I don't know how old I was, but pretty young. I remember that I loved squares and powers in general. And of course, I memorized lots of powers, and of course, I was familiar with the simple powers like 3 squared is 9 and 5 squared is 25. And I remember one time I multiplied 9 and 25 together, and I got 225, and I recognized that that was a square also. I was very excited, and I looked at which square it was. It was 15 squared, and I thought, oh my God, 15 is 3 times 5. This is amazing. 3 squared times 5 squared is 3 times 5 squared. I thought I was a pioneer. I thought I was, had found something magical. So yeah, I was interested in integers ever since I was a small kid. And yeah, it goes way, way back to very, very early. Thank you for bringing that up.
Yeah.
I'm thinking of when you started this program in mathematics, you were just high school student.
Well, I was 15 years old. Yeah, yeah, right. I was a high school student, correct.
But what about your teacher? Was he able to supervise your work?
No, but I had a friend. I had a friend who was exactly my age who taught me how to program. And then when I went to Stanford a year later, when I was 16, I had a mentor in the mathematics department named Gordon Latta, who was a professor of mathematics and a brilliant teacher, a wonderful, wonderful teacher. And I would go into Gordon Latta's office on a regular basis, and he would always welcome me, and I would tell him about things that I had discovered, and he was always so warm and welcoming, and it really made a huge difference in my life. So I think what you're saying is that there was a teacher. It wasn't my high school teacher, although I was on very friendly terms with him, but it was my favorite math teacher at Stanford who played that role. Way up at the top there.
Yeah. Silly question. Is your sweater 40 years old?
It is. It is more than 40 years old. I couldn't tell you where I bought it, but yeah, I of course did that deliberately.
Yes, please.
In your book, and here too, you talk about patterns.
I talk about what?
Patterns.
Currents?
Patterns.
Patterns.
So do you believe that all natural laws are based on some pattern? And there being laws that...
Yeah, well, I am a believer in the beauty. Like I said, the very early the second slide, I believe in the beauty and simplicity of nature as my dad instilled in me, not by telling me or beating it into my head, but just by exhibiting a love for the beauty of nature in everything he did, that it transmitted itself automatically to me. And so, yes. And I think that's a good question to conclude with. So, thank you very much.
Okay, let's conclude then. Okay, thanks.
Thanks.